Now for the topic of logarithmic functions. And in my years of experience, students tend to struggle with logarithmic functions. But all a logarithmic function is an inverse of an exponential function. So every statement involving logarithms is, in some sense, a statement actually simply involving exponents. I'll say at some point that logarithms are exponents. So carefully follow the definitions and you'll be fine. If you can deal with exponential statements, then you can deal with logarithmic statements. So in this section, we'll change exponential statements to logarithmic statements, translate from one to the other and back. We'll evaluate logarithmic expressions, which will require very textbook examples for the numbers to be numbers that we can actually manipulate. And we'll find the domains of and graph logarithmic functions, and we'll solve some limited logarithmic equations. Now, we know that f of x equals a to the x, where a is positive and not 1. This is a one-to-one function. If it's a one-to-one function, then it's got an inverse function. And that inverse function is called a logarithmic function. So the whole idea of a logarithmic function is that it comes to us as an inverse of an exponential function. The formal definition of logarithmic function with base a, where a satisfies these conditions. And we denote this as y equals log base a of x. Y is the logarithm with base a of x. Is defined by the equation y equals log base a of x if and only if x equals a to the y. So the base of the logarithm becomes the base of the exponential. The x that's inside the log function is on this expression outside of the log function. And y, the logarithm itself, is an exponent. So, as I stated, logarithms are exponents in a sense, in the sense explained right here. So, please remember this. This allows you to translate these admittedly kind of weird log statements into not so weird exponential statements. If you can manipulate exponential functions, then you can manipulate logarithm functions because you can translate one into the other. The range of the exponential function, you'll recall from the previous section or two, is 0 to infinity, all non-negative numbers. Well, if that has the log function as its inverse, then that means the domain of the log function is 0 to infinity. The range of a function equals the domain of its inverse function. So we can't take logs on negative numbers. Well, at least if we restrict our attention to real numbers, which from here on out we certainly do. And we can't take the logarithm of 0. We can only take logarithms of non-negative numbers, positive numbers. The domain of the exponential function was all real numbers, so the range of the log function is all real numbers. The domain of one is the range of the other. Now, the logarithmic equation, y equals log base a of x, is just an exponential equation of the form x equals a to the y. So the logarithm, again, is an exponent. The exponent here, the y, is log base a of x. We can do a substitution of y equals log base a of x for y and get the very suggestive statement that a to the log base a of x equals x. Then we can similarly compose the log function with the exponential function inside it and get a similar type behavior. We're dealing with inverse functions of each other. We knew that. That was the very definition of the log function. But we get this little composition of functions, and in some sense, the exponential function and the log function, I want to use the word cancel. They don't actually cancel, they're inverse functions of each other. But what one does, the other one undoes. Whatever log base a did to x, a to the whatever power undid it, leaving us with the identity function here, as you would expect when you compose a function with its inverse, provided x comes from the appropriate place. In this case, it would be the domain of the log function. That is, it would have to be a positive number. So let's look at some examples where we do these translation type things. Okay, number 12 and 18 give us exponential statements and ask us to write them as equivalent statements involving logarithms. 16 equals 4 squared, which is certainly true. Well, remember, y equals log base a of x has as its very definition the equation x equals a to the y. You jumble these symbols around and get this relationship. That's the meaning of the log function. What we've really done is actually solved this equation for the exponent and get this out. That's the meaning of the log function. So here we have, looking at this exponential statement, we've got x equals 16 on the left. The base of the exponential is 4, a equals 4. The exponent is 2, so y equals 2. And then we can take 16 equals 4 squared and rewrite it in this form, y equals log base a of x, with this value of x, this value of a, and this value of y. So we'll get 2 equals log base 4 of 16. 2 equals log base 4 of 16. It's just a matter of taking the definitions and matching up the letters, the x, the y, and the a. Number 18 is the same style, but here we're dealing with e to the 2.2 equals m. That's okay, it's still the same format. We'll take that formula and match it up with x equals a to the y. Here, x would be m, the value that equals the exponential. The base of the exponential here is e, and the exponent itself is 2.2. Y equals 2.2, a equals e, x equals m. So we'll take this x, a, and y, plug that in to convert this to a logarithmic expression. Y 2.2 equals log base a equals e of x, x equals m. 2.2 equals log base e of m. All you're doing is jumbling the symbols around. You're relocating the symbols. So here's converting exponential statements into logarithmic statements. Let's do it the other way around. Let's change this logarithmic statement, log base b of 4 equals 2, to an equivalent statement involving exponents. Same relationship, except this time we've got y equals log base a of x. So here's y, here's a, and here's x. So we'll match this up with this and then produce the exponential function. The base of the log function is b. We've used these symbols where we had the base of the log is a. So in terms of these symbols, a equals b. What's inside the log function is a 4. We have inside the log function in these symbols x, so x equals 4. And the logarithm is equal to y. Here the logarithm is equal to 2, so y equals 2. A equals b, x equals 4, y equals 2. Rewriting those symbols as an exponential, we'll have 4 equals b to the 2. 4 equals b to the 2, or b squared equals 4 in the other direction. So there's how you translate log functions into exponential functions. Maybe for our computational purposes at this stage, that's a more useful thing because we know how to manipulate exponential functions. All right, a couple more along those lines. this says find the exact value without using a calculator for these log statements. Okay. These are of the form the logarithm equals what? Remember, logarithms are exponents. What we're looking for in this first one, verbally, is the exponent we would put on the base 3 to produce the output of 1/9. Here we're looking for the exponent, the logarithm, we would put on the base square root of 3 to produce the value 9. And I see lots of powers of 3 here, so we'll actually be able to do this without a calculator. If they mix the bases up in a weird way, we probably couldn't give precise values with our current knowledge. Well, we'll work this, as previously hinted at, by rewriting the log equation as an exponential equation. We've got y equals log base a of x if and only if x equals a to the y. So match this with this. We've got a, the base is 3, x, the thing inside the log function, the argument of the log function is 1/9, and we've got y equal to that, that's the unknown. Y equals log base 3 of 1/9 can then be rewritten as 3 to the y equals 1/9. Base is 3, exponent is the log, which we don't know. And in that exponentiation, we get x out. X equals a to the y, so we get the 1/9 out. 3 to the y equals 1/9 is how we'll rewrite this, just as we did previously. Now we need to solve this for y. Well, 3 to the y equals 1/9. The only way we can do this with what we currently know is by writing 1/9 as a power of 3. Well, 1/9 is 1/3 squared. Got that 3 squared in the denominator. It can be rewritten as 3 to the -2. So we get 3 to the y equals 3 to the -2. The only way the exponentials can be equal with a common base is when the exponents are equal. That is when y equals -2. Question was, what is log base 3 of 1/9? We had set y equal to that. So we get log base 3 of 1/9 equals -2 to answer their question. We're using the one-to-oneness when we say, hey, if the bases are the same and the quantities are equal, then the exponents are the same. That follows, as we saw in the previous section, from the one-to-oneness of the exponential function. Number 36, same idea. Rewrite the given log base square root of 3 of 9 as an exponential. Here, we've got the base is square root of 3. The thing inside the log function is 9, square root of 3 and 9. We'll set y equal to that. We don't know that value. That's the value we're looking for. So y equals log square root of 3 of 9 can be rewritten as base square root of 3 to the log power, the log is y, the thing we don't know, equals 9, the thing inside the log function. It's simply this translation again with these choices for x and y and a. Well, let's see. Both of these are powers of 3. So we're going to have to take advantage of that so that we can use this one-to-oneness of the exponential function. Square root of 3 to the y equals 9 is the question. 9 is 3 squared. 3 itself is the square root of 3 squared. So we get the square root of 3 squared, or square root of 3 to the 4th power. So we've taken the 9 and manipulated it until we've written it as a power of the square root of 3. Now that we have square root of 3 to the y power equals square root of 3 to the 4 power, we must have y equals 4. By the one-to-oneness of the exponential function, square root of 3 to the whatever power. And we had denoted by y the unknown log base square root of 3 of 9. So the value of that log function must be 4, since that equals y and y equals 4. So it's simply a matter of the very definition of the log function and manipulations of that. Okay, we can only take logarithms of positive things. Here, they ask us, what's the domain of the function? Log base 3 of this thing here. Well, we need this thing here to be positive. Up until this section, when we were looking for domains, we looked for bad things. What can't you do? You can't take square roots of negatives, unless we're having a conversation about complex numbers, and we rarely are, but it did come up. And you can't divide by 0. Well, now you can't take logarithms of non-positive things. So that becomes a brand new and actually our final restriction on with these types of functions. What can't we do? You can't take square roots of negatives, you can't divide by 0, and you can't take logarithms of negatives or 0. So that new condition becomes pertinent with these new functions. The domain of a log function is all positive numbers. So we need that thing inside this log function to be positive. So this becomes a sign test on a rational function. We did this, dealt with this in section 4.3, talking about graphs of rational functions. We'll divide the real number line into intervals using points where the numerator is 0 or the denominator is 0. R of x equals x over x minus 1. This is 0 when x equals 0. The numerator is 0 then, so we'll throw that out. We can't have a numerator of 0 because we can't take logs of 0. And we'll throw out x equals 1. We can't have x equals to 1 or we got division by 0. It's that old problem. So we'll remove 0 and 1 from the real number line, leaving us with negative infinity to 0, open interval from 0 to 1, and open interval from 1 to infinity. So the only place this function is 0 or has an asymptote is at 0 and 1. So throughout each of these intervals, the sign of this function is always the same. So this is when we made the little charts. We chose a test value and saw the sign of the function at that test value. It's that stuff again. Negative infinity to 0. Pick a number in that interval. Negative 1 is the obvious choice. We're going to plug that into this r of x function, called the test value c. We're computing r of c. So we'll have negative 1 over negative 1 minus 1. That's negative 1 over negative 2. It's positive 1/2. The 1/2 part doesn't so much matter. It's the positive part. If it's positive at that value, it's positive throughout this interval. Next interval, 0 to 1. Choose a number in there. 1/2 is the most reasonable thing to choose. Plug that into the function r. We get 1/2 in the numerator. 1/2 minus 1 or negative 1/2 in the denominator. That simplifies to negative 1. The one part I'm not interested in is the negative part I'm interested in. If that function is negative at one point of this interval, it is negative throughout this interval. 1 to infinity, choose 2. We'll get an output value of positive 2, and we have positive throughout this interval. So we have to exclude 0 because that would involve a logarithm of 0, and we can't do that. We exclude 1 because that would involve division by 0, and we can't do that. And we exclude the interval from 0 to 1 because that would involve logarithms of negatives, and we can't do that. So we were looking for where r of x is positive, where that quotient function is positive. It's on this interval and this interval. So the domain of this function in interval notation is negative infinity to 0, union 1 to infinity. That's the domain of this log function. So there's revisiting an old idea, finding domains with a new twist. We found something else we can't do. We can't take logs of 0 and we can't take logs of negatives. Back to the notes. Let's look at graphs. Exponential functions and log functions are inverses of each other. So if we graph y equals log base a of x, we do so by reflecting the graph about the line y equals x, the exponential function y equals a to the x. Well, you know how to graph y equals a to the x. Let's start with this picture on the right. When a is greater than 1, we had exponential functions that look something like this. They always pass through these 3 points. When a was greater than 1, they were increasing functions. They had a horizontal asymptote of y equals 0. These things we learned in the last section. And you know, a function and its inverse are related by reflecting about the line y equals x. So take this y equals a to the x curve in blue, reflected about this line, and get this curve in pink, log base a of x. Y equals log base a of x. The point 1 comma a is mapped to the point a comma 1. You interchange x and y coordinates. 0, 1 is mapped to 1, 0. Negative 1 comma 1 over a is mapped to 1 over a comma negative 1. You interchange x's and y's. There's 3 test values. When we had a between 0 and 1, it was this blue curve here. It was an exponential curve, but it was a decreasing curve in this case. Still had an asymptote of the x-axis, this time to the right, whereas previously it was an asymptote to the left. And this curve is going to cross the line y equals x somewhere. We've got the test values again, negative 1, 1 over a, 0, 1, and 1a. So there's the test values, excuse me, these key points, I think the text calls them. We have these 3 points on the curve, and they get reflected about that line as well, rather similar to what we had before. So this time we get a log function base a when a is between 0 and 1 to look like this. So in pink, we've got this function. When a is between 0 and 1, when a is greater than 1, in pink, we get this for the log function. This has a vertical asymptote of x equals 0. This has a vertical asymptote of x equals 0. Here, curves going upwards towards infinity at that asymptote, x equals 0. Here, the function, if we follow it right to left, is headed downward to negative infinity for this vertical asymptote. In pink, this is a decreasing function. This is an increasing function. We can see the domains and ranges. We already knew those. For example, for the pink function here, the domain is positive real numbers. The range, all real numbers. It's got a vertical asymptote, so we've got no problem that the log function takes on negative values. It cannot take in negative values, but it can give out negative values. And it grows without bound, though it grows very slowly, and we get all possible y values out. The range is all real numbers. We talked about that above. And let's deal with some graphs of these, and then we'll state a little collection of properties of log functions. Graph f of x equals 4 to the x, and graph its inverse function on the same set of axes. We're good at graphing exponential functions. Following the previous section, we know the shape of the exponential function. We know the shape of the log function as well. We could view these as new members of the library of functions. So we'll just plot a few points knowing the shape of these curves and use the asymptotes to get a fair idea of the graph of the functions. If we plug in 0 to the exponential function, we get out 1. 0, 1 was always on these exponential functions. Plug in 1, we get out 4. This is the point 1 comma a when we dealt with a to the x as a function. So there's a couple of points, 0, 1 and 1, 4 on the graph of the exponential function. So the point 1 comma 0 and 4 comma 1 interchange the x and y values in both of these. These will be points on the inverse function, on the log function. The exponential function has y equals 0 as a horizontal asymptote. It has that as x approaches negative infinity, that is to the left. And the inverse function, the log function, will then have a vertical asymptote of x equals 0. We've done interchanging of x and y here. The y became an x, the horizontal became a vertical. So with that information, we get the following. The exponential function, it looks something like this. Passes through the point 0, 1, the point 1a, a is 4 in this case, 2 comma, 16, so we're off the scale there. Negative 1, we get out 1/4, which looks about right. And now we'll take this and reflect it about the line y equals x. So the point 0, 1 will be flipped over to the point 1, comma 0. The point 1, 4 will be flipped over to the point 4, comma 1. We had this horizontal asymptote. Imagine folding that about the line y equals x. That horizontal asymptote will fold over to this vertical asymptote. And the graph of the log function looks something like this. These get really close to 0. The base is 4. So this is going to get really close to that vertical asymptote of the y-axis as well. So there's one of the graphs. Here's a situation where they give us a graph and a whole list of functions and say, match the function with the graph. Okay. Here's the function. It's got a vertical asymptote at x equals 1. They give us several functions here, several log functions. We know log base a of x has a vertical asymptote at x equals 0. So we can eliminate a bunch of them just based on that information. A, B, C, D, E, and H have vertical asymptotes of 0. Yeah, A, that's just a log function. That's got a vertical asymptote at 0, x equals 0. Y equals log base 3 and negative x. Well, it's going to have a vertical asymptote where the argument is 0. This one has a vertical asymptote at 0 as well. This one has a vertical asymptote at 0 as well. If you like, negative x equals 0 or x itself equals 0. Same here, vertical asymptote at 0. This one has a vertical asymptote at 1. Here, we've got a vertical asymptote at 0. The -1 would relate to a vertical translation down by 1 unit, but the asymptote stays in the same place, and that eliminates that one. Here, the log function will be undefined at x equals 0. That's where the vertical asymptote will be. From this, we've done some reflections, it looks like, with a negative sign about the y-axis. But the asymptote remains at x equals 0. And here we've done a vertical translation up by adding 1, but the vertical axis stays at the same place. So take the argument in the log function in all of these, that'll tell you where the vertical asymptote is. So we've eliminated everything but f and g. Let's go to the next slide. F and G both have vertical asymptotes at x equals 1. This will be 0, x minus 1 will be 0 at x equals 1, and 1 minus x will be 0 at x equals 1. So both of these, based simply on asymptote information, vertical asymptotes for logs, F and G are still both plausible. So we need to see what happens in terms of some other property. Let's use the domain. The domain of f is 1 to infinity. We can only take logarithms of positive things. When is x minus 1 positive? When x is greater than 1. That is, when x is in the interval 1 to infinity. And that's the domain of this drawn function, this intended to be log function here. So it looks like f can't be eliminated by that. How about the g function? We need 1 minus x to be positive. Well, if 1 minus x is positive, then x must be less than 1. That is, x must be in the interval negative infinity to 1. The domain of the g function is negative infinity to 1. That'd be to the left of this asymptote. And the function's not graphed to the left of the asymptote, it's graphed to the right of the asymptote. So this is the winner. Part F, choice F, y equals log base 3 of x minus 1. That has this kind of thing as its graph. Oh, with my usual complaints that I'm trusting that the pattern continues. They have indicated the pattern in terms of the vertical asymptote with this function. And if you'll recall from some of our past graphing experience, they gave us curves that were shaped like this. They were foreshadowing these log functions at the time. Let's do another one. Match the graph with the function. Okay, this time we've got a decreasing function. It might be useful. The domain is positive real numbers. The domain of choices B, C, and D are negative real numbers. Let's see, we got negative x. We'll need negative x to be positive, so x itself will have to be negative, right? And that's not the case here. Same story here. Negative x will have to be positive, so x itself will have to be negative. Not the situation here. Log base 3 of negative x, same thing. We'll have to have x be negative, and that's not the case with this graph. So none of those match. The domain of f is 1 to infinity, as we just saw. This is defined for x equal to 1 and less than 1. So that can't be the answer. Wrong domain. G had the domain of negative infinity to 1, as we argued previously. 1 minus x would have to be positive, implying x has to be in this interval. And the function's not drawn on that interval. Small piece of it, but not for the negative values. So that leaves us just with choices A and E, having eliminated the others. Let's see, we eliminate H. I didn't eliminate H. Let's see if we can eliminate this one. It's got the right domain. We've got a, I'm sorry, I'm misreading it. H is going to be the answer. Excuse me, I'm going to eliminate A and E. Choices A and E are A and E. It says they're increasing functions. Yeah, this is just a log function. You know, log functions are increasing. E, this is a log function that has been vertically translated down. Well, the vertical translation doesn't affect increasingness. So both of these will be increasing. So now we've eliminated A, B, C, D, E, and F, and G, and that only leaves H. So H must be the answer by process of elimination, but let's look at it a little more forensically here. If we started with log base 3 of x, log base 3 of x would look something like this. We'll put a negative sign in front of it. That'll flip it over and make it look something like this. Then we're going to shift it up 1 unit. It'll look something like this, shifted up 1 unit. It's hard to tell on the scale exactly what they've done, but this certainly has the right shape. It's got the right domain. The negative sign in front of the log function means it would be a decreasing function. We changed it from an increasing to a decreasing function with a negative sign there by reflecting it about the x-axis. So if any of these are the graph, it must be H. If any of these are the equation, it must be H. Returning to the notes and stating some properties of logarithms. So here we're combining both a between 0 and 1 and a greater than 1, those two sort of categories of log functions. In a list of properties of log functions, though we will have to delineate between a greater than or less than 1, and at least in the increasing decreasing case. Domain is a set of all real numbers, all positive real numbers for log functions, because that was the range of an exponential function. As discussed above, the range was all real numbers because that was the domain of the inverse function, the exponential functions. Domain, positive real numbers, range, all real numbers. The x-intercept is 1, and there is no y-intercept. I got my eye on these pictures. Yeah, x-intercept's right there at 1, 0, 1, 0, whether a is greater than or less than 0. No y-intercept, right. They actually had vertical asymptotes along the y-axis. We'll state that here shortly. So no y-intercepts. The y-axis, in other words, the vertical line, x equals 0, is a vertical asymptote. And the curve approaches that vertical asymptote. Does it approach positive infinity or negative infinity? This list of properties didn't address that, but it approaches positive infinity when a is between 0 and 1, and it approaches negative infinity when a is greater than 1. Just one is pretty much a reflection of the other about the x-axis. The log function f of x equals log base a of x is decreasing when a is between 0 and 1, as we saw in the picture, and it's increasing when a is greater than 1. So this is the only bit of these properties where we had to delineate between a being greater than 1 or less than 1. The graph contains the points 1, 0, a comma 1, 1 over a comma negative 1, as we've seen, and sort of taking Sullivan's word on this. The graph is smooth and continuous with no corners or gaps. We can't really address these ideas of smoothness and continuity without calculus, but I'm happy to accept Sullivan's word on that and deal with it in more detail in calculus. And so we get graphs that look like this. Log function looks like this, vertical asymptote over here, decreasing when a is between 0 and 1, vertical asymptote along the y-axis, and increasing when a is greater than 0. Okay, we're interested in logs base this number e. We encountered the irrational number e as 2.71828 something or other in the previous section when we talked about the natural exponential function. E to the x, where e is that weird number there, is the natural exponential function. What's natural about it? We have to sit tight for calculus. That will be explained in the calculus setting. What's natural about it is a calculus property. So for now, we'll just deal with it as yet another function in this pre-calculus class in preparation for calculus. So we had a natural exponential function. Then the natural log function would be the inverse of that function. Let's define log base e of x as the natural log function, commonly denoted ln of x. So instead of writing log base e of x, it is common in calculus classes and pre-calculus classes to write that as ln of x. Maybe this is a common notation in physics classes as well. In upper level classes, you'll use a different notation, but for the next year or two, you should see natural log functions referred to as ln, n for natural. So we have y equals the natural log of x if and only if x equals e to the y. This is simply a translation of the definition of log function when the base is this number e. The graph of the natural log and the exponential functions together is given here. We know what the exponential function looks like. It grows like crazy, approaches asymptotically the x-axis to the left. Reflect that about the line y equals x, and we'll get the now familiar shape of a log function. Natural log function looks something like this. It always passes through the point 1, 0. It has this vertical asymptote of x equals 0, the y-axis in the downward direction. And the three key points are kind of messy because they involve this number e and 1 over e. And it's an irrational number with an infinite decimal expansion. So we'll simply denote it as e. It's around 2 3/4. So that'll have to do in terms of plotting things by hand. Another logarithm that you may encounter in some settings is called common logarithm. The common log function is log base 10. Sometimes that's denoted simply as log of x. They don't write the base down, since we have a base 10 number system. Base 10 logarithms seem like a common thing to do, maybe even a natural thing to do. But natural, that word is saved for base e log functions. So common logs, logs base 10, we will use these very little. They'll only come up in passing. Certain scales are log base 10 scales. The Richter scale is a base 10 scale. Decibel scales for loudness of sounds is a log base 10 scale. So these do arise out there. We know we could then take y equals the common log of x and rewrite that as the exponential statement y equals 10 to the x power. The graph of the common log function and the base 10 exponential function look like this. Passes through the point 0, 1, -1 1/10, 1 comma 10. So it's kind of, approaching off the scale here. So they've only graphed a couple of points, and this grows like crazy because the base is big. 10 is a rather big number. By the time we reach 4 over here, we're at 10 to the 4th power. So we're 10,000 units up. So on this scale, what is that? I don't know, tens or dozens of feet that way. And when we reflect that curve about the line y equals x, gives us the common log function, log base 10 function, as given here. Same shape. The only subtleties is the steepness of these curves. Couple of examples to illustrate that. Consider f of x equals natural log of x minus 3. Find the domain, graph it. From the graph, determine the range and asymptotes of this function. We could already figure that out algebraically. Find the inverse of this function, which would be an exponential function. Find the domain and range of the inverse and graph the inverse. Okay, so maybe we'll pick some of that information up as we go. Log functions have domains 0 to infinity. So we need x minus 3 to be greater than 0. In other words, x minus 3 is greater than 0. In other words, x is greater than 3. So the domain of the given function is 3 to infinity. We can only take logarithms, even natural logarithms, of positive things. So that requires x is greater than 3 in the formula. That's the domain. By the way, that'll be the range of the inverse function, because a function and its inverse behave like that with respect to domain and range. Let's graph by starting with the natural log function. I'll say that, I guess that's in our library of functions, and we'll replace x by x minus 3, x minus h, or x minus 3, where h is 3. And this gives a horizontal shift to the right. It's to the right since the h parameter is 3. The parameter is positive. Maybe go back and look at the sections on transformations that we dealt with, and I think it's in chapter 2. So translation to the right by 3 units of the natural log function. The log function contains the points 1, 0, and e1. So we'll try to plot those as best we can. It's a little more awkward with these irrational numbers. But log function looks something like this. Here's the point 1, 0. Here's the point e, comma 1, around 2 3/4 for the x value. It's 2.718 something or other. And we get the natural log function to look something like this on this scale. And then we translated it to the right by 3 units. So this point will move to the right 3 units. This point will move to the right 3 units. The vertical asymptote will move to the right 3 units as well. And so we get a vertical asymptote of x equals 3. Yeah, we could have guessed that, given the algebraic formula. So we see from the graph, the range, the output for this function in red is all real numbers. This grows without bound. It does it really slowly, but it does not have a horizontal asymptote. It grows without bound, just as the exponential functions have a corresponding behavior. And the vertical asymptote is x equals 3, as we stated. Part D, they want the inverse. Well, f of x, natural log of x minus 3, we could solve for y, or replace f of x with y, I think was our first step in finding inverse functions, and we get y equals the natural log of x minus 3. I tell you what, let's rewrite that natural log as log base e. So then we get interchanging x and y, x equals log base e of y minus 3. And this looks more like what we were dealing with previously. The base is e, the exponent is x, and then we've got the y minus 3 parameter equal to that exponentiation. So x equals log base e of y minus 3 translates into e to the x power equals the stuff inside the log. E to the x equals y minus 3. What we're doing is solving for y here. We're in the process of finding the inverse function. So we've interchanged x and y. That's led us to this. Solve for y. That gives us y equals e to the x plus 3. And so that must be the inverse function. There's the inverse function. Part E, they want the domain and range of the inverse function. Well, that's easy enough. The domain of the inverse function will be the range of the original function. The range of the original function was all real numbers. It's a log function. That's the range of a log function. The range of the inverse function will be the domain of the original function itself, with the restriction that we can only take logs of positive numbers, led us to the domain of the open interval from 3 to infinity for f. So the range of f inverse is the open interval from 3 to infinity. The domain of a function is the range of its inverse. The range of a function is the domain of its inverse. And in part F, they want us to graph it. All right, so we'll start with y equals e to the x. This is the function we're going for. Here's the exponential function. E to the x passes through the point 0, 1, passes through the point 1, comma e. So here's 2 3/4-ish. Has a horizontal asymptote, draw it in blue to color code things. And to produce the inverse function, we simply need to add 3 units to the exponential function. Adding 3 corresponds to a shift up by 3 units. So simply take this point 3 units up, this point 3 units up. Horizontal asymptote goes 3 units up as well. And the graph of the inverse function, 3 plus e to the x, must look something like this. So we're just rehashing things we've done in the past, domains, ranges, graphs, using these new functions, the exponential functions and the log functions. Another one involving a common logarithm. Consider f of x equals 1/2 common logarithm of x minus 5. Find the domain, graph it. From the graph, determine the range and any asymptotes, find the inverse function, find its domain and range, and graph it. So same instructions as the previous one, this time with a common log instead of a natural log. Log functions have domains of 0 to infinity. This is a log function with some additional slight arithmetic that doesn't change the domain. So the domain of this function is all positive, real numbers. 0 to infinity, the open interval. Graph it. Okay, let's do it with transformations. We'll start with the library of functions graph, y equals common log of x. First, we'll multiply by 1/2, which gives a vertical compression by a factor of 1/2. Vertical compressions are quite hard to illustrate in this stuff, so we'll do our best. So we'll compress vertically by a factor of 1/2 the log function. That'll give us the 1/2 log x, common log. Then we need to subtract 5. Subtracting 5 is equivalent to a vertical shift down by 5 units. So we'll start with y equals log x. We'll compress by a factor of 1/2, and then we'll shift down by 5 units. Some key points are 1, 0, and 10, 1 on the log base 10 function, the common log function. So here we go. In blue, we've got the log function. In green, we've multiplied all function values by 1/2. So the green function is supposed to correspondingly have points 1/2 the distance from the x-axis. Looks like the scale's off a little bit over here on the right. The green point should be 1/2 as far from the x-axis as the blue point is. That should be the case correspondingly with all these points till we get to the point 1, 0. They both pass through that point. And we have a similar behavior below. Quite difficult, as I've said. It's difficult to reflect this vertical compression and vertical stretching stuff. But we get a relationship between the green one and the blue one of something like that. And then we needed to take the green one and shift it down 5 units. So this point goes down 5 units. This point goes down 5 units. Vertical asymptote stays the same. or if you like, it moves 5 units down, but that doesn't change the vertical asymptote. And so the function we were interested in, 1/2 common log x minus 5, looks something like the function in red. We see from the graph that the range is all real numbers, grows without bound. Eventually, this curve will reach the x-axis. Eventually, it'll reach all heights. It just grows very slowly, especially base 10. As a vertical asymptote was part of the question in part C, vertical asymptote of x equals 0, the vertical line x equals 0. In other words, the y-axis. Part D, find the inverse function. Okay, we'll use our inverse function finding technique. We'll replace f of x with y, write it like this, interchange x and y, as you would do with an inverse function, to convert this equation to this equation. X equals 1/2 common log y minus 5. If you like, 1/2 log base 10 y. So I want to deal with this in terms of exponential, converting it to an exponential function, exponential base 10. Okay, we're trying to solve this for y. Excuse me. First, let's get the log function by itself. We'll add 5 to both sides. Looking at the far left here, we get x plus 5 equals 1/2 log base 10 of y, or, well, cross multiplying by 2, 2 times x plus 5 equals log base 10 of y. Okay, so 2x plus 5 equals log base 10 of y. Convert this log function into an exponential expression. We've got this equals log base a of that. That means the base to this, the left-hand side, equals what's inside the logarithm. Y equals 10 to the 2x plus 5. It's that AXY stuff that we had before. Simply translating the log expression into the log equation into an exponential equation. Ooh, and we got y by itself, and we were trying to solve for y. So that gives the inverse function as 10 to the 2x plus 10 power. The inverse of a log base 10 function is an exponential base 10 function. So no surprise on the format of it there. Domain of the inverse function is an exponential function. Exponent could be anything. All real numbers are good. The range, what will come out of an exponential function? Only positive things. Exponential functions never took on the value 0. They were never negative. And so the range is all positive numbers. And we could correlate this with the range and domain of the original function f, the inverse of the given function. And we want a graph. So we'll take the key points 0, 1, and 1, 10 on the blue graph. Here we've got a 10 to the x function. What we're going to do is replace x with x plus 10. Replace x with x plus 10. That corresponds to a horizontal shift to the left by 10 units. So in the blue curve, we've shifted it to the left 10 units. This is where the key points come in useful. So this point at 0, 1 has gone to the point -10, 1. It's moved to the left 10 units, that transformation. Now we're going to replace x by 2x. We're going for this function. So replace this green x with that red 2x. That has the effect of a horizontal compression. We haven't done many of those in examples, a handful. Horizontal compression by a factor of 2. So we're going to take all of these x values and halve them. And it's really hard to see that that's what's happened. It looks like we just shifted this thing to the right. That's not what we did. It's a compression. We've taken this distance from the green point to the y-axis and halved it. We've taken this point, this one's easier to deal with. It's distance -10 from the x-axis, and we've halved it to -5. So all these green points have been brought closer to the y-axis by a factor of 1/2. They've all been halved, and they're horizontal distances, remember. So that's why we get the horizontal compression terminology. And as best as we can do, the curve in red is a reasonable drawing of the function f of x equals, f inverse of x equals 10 to the 2x plus 10 power. Returning to the notes, equations that contain logarithms are called logarithmic equations. Care must be taken when solving logarithmic equations algebraically. Remember, if we have log base a of x equals m, a must be positive and not equal to 1. The input must be positive. Actually, this is incorrect. That should read x. X, the input of the log function, must be positive as well. The output, this is incorrect. I'll get this corrected in the notes, should read x. The input has to be positive. The output could be anything. The range of a log function is anything. So log functions, maybe we can change the log expression into an exponential expression, going back to this again. And without a calculator, we'll sometimes just have to leave the answers in terms of log statements. We'll have a way later to deal with it. It depends on what the base is. Even with a calculator, we don't have the ideas of how to take logs to particular bases. Base 10, there's a button on the calculator, and base E, there's a button on the calculator, but there's not a log base 3 button on the calculator. So even with a calculator, we don't have ways to deal with this in its entirety just yet. So let's go through several examples. First, solve these equations. Okay, these won't take particularly long. Remember, y equals log base a of x can be rewritten in this exponential statement, a to the y equals x. So you want to solve for x in log base 5 of x equals 3. Log base 5 of x equals 3 means the base 5 to the other side of the equation, power y, 5 cubed equals x, the thing inside the log. Simply following this pattern again, x equals 5 cubed, 5 cubed is 125. There's the answer to that one. Second one, natural log of e to the negative 2x equals a. Okay. Natural log function is log base e. So let's take this and rewrite it as log base e of e to the negative 2x equals a. That you're more familiar with. It's the only reason I'm rewriting it like that. Now it looks exactly like this, and we can pick the letters off and rewrite this as the base to the right-hand side equals the stuff inside. E to the 8th power equals this, e to the negative 2x. Why, here we've got the same base and equality, so the exponents must be the same because exponential functions are 1 to 1. We must have 8 equals negative 2x or x equals negative 4. So we solve that one. Of course, these are set up to be solved with a little bit of knowledge that we have about logs and exponentials. Number 102. Solve e to the negative 2x equals 1/3. Okay. We're trying to get to x, so we're solving for x. How are you going to get the x out of that exponential function? Well, let's rewrite it as a logarithmic expression. This means log base e of the right-hand side equals the exponent. Log base e of 1/3 equals negative 2x. Now we can get to the x. The only thing in our way is a negative 2. We'll divide both sides by negative 2, and that will produce x equals negative 1/2 of this, negative 1/2 log base e of 1/3. If you like, negative 1/2 natural log of 1/3. So we were able to solve that one. I don't know a numerical approximation for the natural log of 1/3. We do have a natural log button on the calculator. For now, we're just going to leave it like that. This is the exact value, even though I don't know numerically what this is. Number 112, 4 e to the x plus 1 equals 5. 4 e to the x plus 1 equals 5. Let's divide both sides by 4, and we get an exponential function equal to a number. This can be rewritten in terms of a log function as log base e of 5/4 equals the exponent, x plus 1. Log base e of 5/4 equals x plus 1. We're solving for x, so we'll subtract 1 from both sides and get x equals log base e of 5/4 minus 1, or if you like, natural log of 5/4 minus 1. That's the precise value. I do have a natural log button on the calculator. Let's save that for later with calculators. We'd have to do all this work anyhow, even if we had a calculator. It would just be additional work. And finally, a little word problem of sorts. It deals with probability. It says between 5 p.m. and 6 p.m., cars arrive at Jiffy Lube at the rate of 9 cars per hour, that is 0.15 cars per minute. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 5 o'clock. F of t equals 1 minus e to the negative 0.15 t. T is measured in minutes. There's where that 0.15 parameter comes in, apparently. So a little problem related to probability. We don't need to know where this came from. We'll just take this as the given function. They say determine how many minutes are needed for the probability to reach 50%. Determine how many minutes are needed for the probability to equal 80%. So their questions are, when does f of t equal 50% or 0.5 or 1/2? Here's the function. We'll set it equal to 1/2. Let's manipulate those numbers there and solve for t. T is stuck inside an exponential function. It will take a log function to get to it. So let's subtract 1/2 from both sides. That'll give us a 1/2 over here. Let's take the exponential to the other side, so it'll become positive. And we get e to the negative 0.15 t equals 1/2. You like that? That's a to the y equals x. So translate that into a log function, or is it a to the x equals y? Translate that into a log function. We'll have log base e of the right-hand side equals the exponent. Log base e of 1/2 equals negative 0.15 t. Written in terms of ln notation for natural log. Natural log of 1/2 equals this. Divide by the negative 0.15 and we get t by itself. We get t is negative 1 over 0.15 times the natural log of 1/2. We'll whip out the calculator. It has an ln button on it. A scientific calculator does. They're built into Microsoft Windows, for example. Make sure you use the scientific calculator, though. It's not in the standard one. And crunch the numbers, and we get 4.621 minutes. So the probability is 50% that a car will show up in the first 4.621 minutes. But there's a 50% probability that it won't. When will the probability reach 80%? That you're 80% probable for a car to have shown up? Well, same idea, same formula, same technique. We'll end up with 80% gets subtracted from 1 to give us 20%, 0.2 or 1/5. So we get 1/5 where before we had the 1/2. Otherwise, the computations are identical. And a calculator tells us 10.7 minutes. It took longer for you to be more certain that a car would show up, and that should seem intuitive. So there's a little example and a manipulation with calculators, though I didn't show you the keystrokes. Straightforward. You're good with calculators, I trust. And that completes the introduction to and some elementary, very elementary properties of log functions. Actually, we primarily turn log functions into exponential functions. In the next section, we'll look at properties of log functions per se and do some similar manipulations, but do them slightly differently. I'll see you in the next section, 5.4, I think it is, 5.5 maybe. Yeah, I'll see you in 5.5 here shortly. Have a nice day. Bye.